Great. Hi everyone. If I haven't met you yet, I'm Maya Fishbach. I'm currently an assistant professor at the Canadian Institute for Theoretical Astrophysics, CITA, at the University of Toronto. And this is going to be a series of 3 lectures today, Thursday, Friday, I believe, about some of the astrophysical implications we can learn by studying gravitational waves from the stellar graveyard. So what I mean by that is really stellar mass black holes and neutron stars, although I won't talk too much about neutron stars. But of course, the stellar graveyard is also in reference to this famous figure, which shows the masses of black holes and neutron stars that we've detected, mainly in black holes and gravitational waves in blue, and then some electromagnetically known stellar mass black holes, and then neutron stars down here, which is still mainly we know about from electromagnetic observations. And now that if you haven't seen this plot yet, now that you've seen it, you have to put it into every single talk you give from here on out. I don't make up the rules. So, is this not? Okay, maybe this died. No. Okay, it does work. Okay, so I'll basically be telling you today will be about observations and how we can do binary black hole population inference. Lecture 2 will be more on the theory side and what we know about the astrophysics of binary black hole formation. And then on Friday, I will talk about just putting those things together and what are some of the astrophysical lessons we've actually learned from the black holes we've observed with the LIGO, Virgo, Kagra gravitational wave observatories. So starting today with the population of merging stellar mass black holes, I'll talk about how we can infer merger rates, what we know about the mass spin redshift distribution, and then also how to fit a population in the presence of measurement uncertainty and selection effects, also known as hierarchical Bayesian inference. So we do a population analysis because we have a lot of events that we're trying to understand as a population. And so this plot just gives you a sense of how many events we've detected in gravitational waves to date. This only shows events reported by LIGO, Virgo, Kagra, and this is observing time and the cumulative number of detections. So the takeaway is that as of yesterday or 2 days ago, I don't know what date it is, I pulled this on July 21st, we had 303 likely gravitational wave events. Most of these have not been published yet. Everything in gray has not actually been published yet. And so 300 is a lot of events. That's just too many to analyze them all individually. I personally lost track of the names of individual events after we hit around like 30 events, which I think is still pretty good. But still, the best way to study the events at this point is to look at them as a population and to tease out astrophysical inference from the population of sources. And we've already learned about how these gravitational wave signals from these types of binary black hole sources encode the properties of the source. So the first thing that's encoded in the gravitational wave sources is how big each of the black holes in the binary is. We label the bigger one as M1 and the smaller one as M2. Then we also learn from the gravitational wave signal about the spins of the black holes, how fast they're spinning and what the spin orientation is relative to the orbital angular momentum axis and relative to the 2 black holes. And then we also measure the luminosity distance to the source, which, if we know cosmology, tells us the gravitational redshift of the source. And that allows us to translate from detector frame masses to source frame masses. It also tells us how old the universe was when the source merged, and allows us to learn about the evolution of the population of black holes over cosmic time, for example. So all these properties together when we look at them on a population level, are telling us how, when, and where black holes are made. And so in the earlier lectures by Teja and Neil, for example, we learned about how to analyze individual events through parameter estimation techniques. So when we just have a single gravitational wave detection, we've made the detection. We know there's a gravitational wave signal of interest that's in the detector noise. We can infer things like the M1 and M2, right, the two masses, the distance to the source, the effective in spiral spin here. So we can do this for an individual event. And then also, so if all you have is one event, how might you go about estimating the rate? And so this is not super relevant when we have 300 events, but sometimes we still have an event that we're maybe not sure is part of the population. So we still do this single event rate estimate, but it's also illustrative for the many event rate estimate. So, okay, so I have some sort of math here and then a plot here. But basically, the expected number of events is the merger rate times this VT factor. And so the merger rate has units of inverse volume, inverse time. It's a number of mergers per some co-moving volume per some source frame time. And so VT has units of volume times time. And so when you multiply them together, it's dimensionless. The observed number of events, which is our data, that's what we've measured, that is distributed according to a Poisson distribution with centered on the expected number of rates. So the mean of the Poisson distribution is the expected number of rates. Standard deviation for a Poisson distribution is the square root of the expected number of events. And you can just write that Poisson distribution for people who don't remember as this expression here, where R times VT is just the expected number of events and N obs is the number of events that we've observed. And so this is like the likelihood for the number of observed events, which is our data, given the rate, which is the parameter we're trying to infer. You can easily turn that into a posterior using Bayes' theorem, the posterior on the rate, which is what we're trying to infer here, given N obs, which we know is proportional to the prior times the likelihood. Okay, and so this VT term is something that we estimate with injections, which are simulated signals that we inject into real detector noise. And so this plot is from the third gravitational wave transient catalog paper. And it is just showing pretty much the same thing in 6 different panels. This is really the one to focus on. It's the different panels are just for the different search pipelines that the LIGO Virgo Cogra or LVK collaboration uses. And I think it's very hard to read, but basically this color scale and also the number in these circles is giving you the sensitive volume for a binary black hole with masses that fall on whatever the X and Y axis is. So really, as you just go to higher masses, you have a larger sensitive volume to binary black holes with those masses, because larger mass binaries emit louder gravitational waves, and so we can see them to a higher volume. Going into a bit more detail, and now I've just cut off that first panel, so maybe now it's easier to read. But basically, if we have just a single event, so I guess this VT factor here depends on like your population. What sort of signals are you talking about, right? What sort of masses are you talking about? And then the population assumptions are going to affect what this VT is. You can expand out for just like two fixed black hole masses with two fixed spin vectors, so M1, M2, chi1, and chi2. This VT term is just an integral over redshift. So you multiply the time you've been observing, T obs, and then you have to calculate what the probability is, or what fraction of sources with these masses and spins would you detect at a given redshift. So you're imagining, for this calculation, you're imagining that sources of some masses and spins are just randomly distributed uniformly in co-moving volume and source frame time. And so this sensitive volume is just going to be given by how likely you would be to detect something with those masses and spins at a given redshift. And then at each redshift shell, you just assume that the number of sources is proportional to the co-moving volume times this 1 plus z, 1 over 1 plus z term, which is the conversion between source frame time and detector frame time. So we're assuming sources are uniformly distributed in source frame time, which because of time dilation is not the same thing as uniformly distributed in detector frame time. Like in some redshift bins, time will tick slower than other redshift bins. So it's just this integral over redshift. And then if you are just estimating the rate of a single event and you are in the LIGO-Virgo-Cogra collaboration, you will use this method called KKL after this paper by Kim, Calagera, and Lorimer from 2003, which assumes that the population, that you only have one event, but you don't exactly know the masses and spins of that event. So you assume that that one event is really representative of a population distributed according to the posterior that you get from the parameter estimation for that event. So this is the posterior here that you just gotten from the parameter estimation. Now I've just replaced M1, M2, chi1, chi2 with this theta because it's shorter. And then so you just integrate out, this is missing a d theta term, but you just like marginalize over your VT that you get for every M1, M2, chi1, chi2 in your posterior, and you marginalize out the unknown theta with the posterior. So then you just have this as your VT, and you use like this previous expression to estimate the rate given this VT. So yeah, this is not really a realistic assumption because we don't have a population of sources distributed according to the posterior of your event. This is just something that you do when you only have one event. Okay, so now we can kind of switch gears to talk about the case of all of the events in a catalog. And so the first step that you would do for a population inference is you still need to know what the properties are of each event individually. And so you start with single event parameter estimation. That's just what is shown here for some subset of events, right? And M1 and M2, each one of these contours, both the ones that are in color and the gray ones in the background, show the 90% credibility contour for where these individual events lie in primary mass, secondary mass space, and then also in chi-effective, this effective in spiral spin versus chirp mass space. So they're kind of all over. It's really hard to learn anything just from like squinting at this. I mean, you can learn some things, like there don't seem to be a lot of unequal mass events, but that's not super informative. So what we really want to do is learn about what the population of these events mean. And by that, I mean, what is the merger rate density as a function of black hole masses and spins and redshift? And so to do that, a first step is to introduce a population model that describes the distributions of masses, spins, and redshifts across multiple events. So a first example you might think of if you are an astronomer and you love power laws, as Chiara explained yesterday, right? Astronomers love power laws. So you could fit a power law to black hole masses. And so that would look something like this, where you have the rate density as a function of black hole primary mass. And this is a power law distribution with some free parameters, for example, the minimum mass, the slope of the power law, the maximum mass, and then just what the merger rate is, which can move this up and down. And then when you do this, when you try to infer the minimum black hole mass, the slope, the maximum mass, the normalization, you have to take into account the measurement uncertainty right from the fact that we don't perfectly measure like the masses and spins of these events. We have these pretty large error bars. And you have to take into account the selection effect. So that's like the VT that we were just talking about. And so, yeah. So here's an example where we actually fit, well, this is like a very old, not interesting example at this point, but using the first 10 binary black holes, we actually fit a power law, right? And so what you end up getting is a bunch of these posterior draws. So this is showing a bunch of different curves on top of each other. If you can follow some of these individual curves, that's just one draw from the posterior that we infer on the power law. So each one of these curves has some minimum mass, some power law slope, some maximum mass, some merger rate. And so each one of these traces is a draw from the posterior, and you infer something like this, right? The black hole mass distribution could look something like this. One thing that came out of this analysis is that it seems that the maximum mass was around 40 solar masses from this power law fit with only the first 10 events. We know that's not true anymore. Okay, so how do we actually do that? So this is the hierarchical Bayesian inference formalism. So before we kind of simplified things and we just had this Poisson distribution for the number of events given the rate and this sensitive volume. When we are actually trying to simultaneously fit for the rate and the shape of the population, then it becomes a little bit more complicated, but the general, if you just squint at this is still just a Poisson distribution. It's just that now we can simultaneously fit the source parameters theta and the population hyperparameters lambda. So theta are like the masses and spins and redshifts of individual events. Lambda is the parameters that are common to all of the events. So like the power law slope that describes the mass distribution, for example, that's just one parameter that all of the events have in common. So that's the distinction between the source parameters and the hyperparameters. If you have some population model, which just gives you the number of events per bin in theta, that's really the thing you're trying to learn, is just like how many events do I have in each mass and redshift and spin bin. So that's this dn d theta, and we just parameterize this like as a power law, for example, with these lambda parameters. Okay, so we have these k-obs, that's the number of events we've observed, which means that we have data from each of those k-obs events. We have theta from each of those k-obs events. That's like k-obs chirp masses and effective and spiral spins and whatever. And the distribution, the probability distribution for those two things jointly, given lambda, which is what's describing the population, is proportional to this, it's this inhomogeneous Poisson process likelihood. The inhomogeneous part comes in because rather than just having a single rate of all black hole mergers, you have a rate of black hole mergers that varies depending on the theta bin you're talking about. So you have more, the merger rate is like higher for 10 solar mass black holes versus 30 solar mass black holes. So that's why it's inhomogeneous. And so here, this is similar to like the VT times R term we had before. This is the expected number of observed events given the population described by lambda. This is the thing that's encoding your selection effects. This is the parameter estimation likelihood for a single event. That's what's encoding the measurement uncertainty. And this is just your population model given your lambda. And so you just have a term like this for every data I and theta I in your set of observed events. You multiply them all together, and then you have this exponent term where the expected number of events is similar to what we had before. I've expanded it out a bit here. So this is, right, your population model. This is the probability of detecting an event with given some data, because the selection only depends on data, but then the data depends on the true parameters theta. So this is this integral over theta and data. Another kind of expression you will often see for the hierarchical Bayesian likelihood is in cases where you're only interested in the shape of the population, or sometimes you can just do this for computational convenience. You can marginalize over the merger rate with some suitable prior. And if you do that, you will get a posterior just for the shape parameters. So what I mean by like shape of the population versus the overall rate is you can write your population model dn d theta as just n, which sets the overall normalization, and then p of theta given lambda, which is like a normalized probability distribution, like a power law, right, which tells you what, or a Gaussian, for example, which tells you how the theta are distributed. And then you can just essentially marginalize over this n. So you're only fitting for like these shape parameters, and then you'll get an expression that looks something like this, which is nice because if you had no selection effects, you would just, this is like very similar, right, to what you just get for the single event PE likelihood, where now this P theta given lambda is like what you called your prior if you were just doing single event PE. And so you can think of a population inference as finding the best prior that you should use for your events, because rather than using like flat prior on detector frame masses, what you're doing is fitting for the best prior. So the population, and the best prior just means like the actual distribution that the masses of your events are distributed according to, which is not flat in detector frame masses. That would be super weird of the universe to do. So yeah, so and then you kind of like end up normalizing this by the detection probability, or like the VT given a lambda. And what this ends up doing is finding the choice. So for lambda that would yield like a higher number of observations, you downweight those because you know that you that you just like see more high mass events, not because they're more common in the population, but because they're easier to detect. So you kind of like downweight populations, which will give you more high mass events because you know that that's like your selection effect. So that's what this term ends up doing. And again, here I've just been showing like the joint probability for data and theta. If you want your likelihood on lambda, that's just going to look like p data given lambda, then you would marginalize over theta. And then if you want your posterior on lambda, you would just multiply your likelihood by a prior. So hopefully that kind of makes sense. I am happy to chat more about this at any point and like walk through the math in more detail and, you know, like the derivations for the inhomogeneous Poisson process likelihood and have some practical examples also. But for now, I thought I would pretty much move on to show you some of the population inference we have. I guess just after one more thing. So like I talked about the selection effects, here's another maybe simpler way of seeing that than the VT plots with the circles and like the green and yellow colors. If you have your like VT as a function of total mass, it'll end up looking something like this, which is another way of seeing that the bigger black holes are louder than the smaller black holes and will give you a higher VT. Okay. Oh yeah, before I move on to more population results, another aspect which I kind of mentioned before about population inference is it's telling us like the prior that we should have used in the single event parameter estimation. So it's also updating our knowledge of the parameters of individual events. And the more events we have in our catalog, the better the more information we have about the individual events also. Like as we're learning the population, we're better learning about the individual events that make up the population. So I think that's kind of intuitive, but one way to see that is that this is one event from this paper. I think this event is GW 170729, if that means anything to you. But this event had a pretty high source frame mass that we inferred in the default parameter estimation. So that is shown in orange in terms of the source frame mass and also the mass ratio that we inferred. And that's parameter estimation just uses some default priors. So, right, it's just flat in detector frame masses. The luminosity distance prior was like uniform in luminosity distance cubed, just kind of arbitrary priors. What we end up using for the population inference is the likelihood of the parameter estimation likelihood, like p data given theta. And we infer the prior we should be using. So we end up getting a posterior that is different. In this case, the posterior we inferred using our population prior was favoring much lower, like things kind of at this side, so lower masses than the default prior, so closer to 40 rather than like 50, and also more equal masses than what we got in the default prior. Of course, this prior was based on the population inference of the first 10 events. So now if we redid this inference with the 300 events, we get something different for our best guess of the parameters of that individual event because our knowledge of the population is constantly evolving. Great. So, okay, how do you actually choose a population model? Hopefully I've convinced you. Oh, yeah, sorry.
So in the previous slide, you said that the answer changes now.
Yeah.
So is it closer to the default or what is it?
Oh, yeah, I haven't actually done it, but I would guess that it would be like it would probably be closer to the default just because in the first 10 events and using this population model, we inferred that the rate dropped off very precipitously above like 45 solar masses. And now we know that I mean, it would probably overall look pretty similar, but we know that there are some events that are 60 and 70 solar masses. So it might be like less of a dramatic push towards the lower masses now. Similarly for mass ratio, in this catalog, we only had equal mass systems pretty much. So we inferred with our population model that Q was always close to 1, and now we know that's not always the case. So it might look a little bit more like the default. But yeah. Now we don't really care. At the time, this event was like a very interesting event because it was the most massive thing we've seen. And obviously now it's like, oh, 50 solar mass black hole, we don't, that's normal. Okay, are there any other questions? Yeah.
Similar question. I'm not in the population analysis game, I've never done it before. But let's say that now I do a similar analysis and I get the top. Is there a way for me to understand how much, and I get like what's the uncertainty? And for example, I guess that once we have 1 million events, we'll say, okay, like we're pretty certain of all the results. But like, but nowadays, if there's like one crazy event, it still change our thing. So like what should give us a feeling that this graph will look again? Is the real deal? What's the uncertainty?
Yeah, so I would say that like the reason I think that this might change with newer data is not really because of the newer data. It's because the population model that was used here was overly restrictive, and we know now that that's a bad model. So in general, if you have a flexible enough model where you could fit the population, like you had a good representation of the population with the model, and it was I guess just like a flexible enough model. As you add more data, your posteriors also on the individual events will only improve. So this type of posterior, I don't have a plot for it here, but you can really see it's coming from this joint inference, really. Like you can write a joint posterior over the thetas and lambda, and then in a plot like this, you really just have you could plot the joint posterior like a high dimensional, like you could make a corner plot of your population parameters versus your masses for an individual event. And then as your posteriors on the population parameters tightened, your posteriors on the individual event would also tighten. But that requires having a population model that is adequate to fit the data. And right now, the population model that was used here was like this power law with sharp edges, and that's just a bad model. So that's why it would shift. Yeah.
Going off on the same question, like then in that case, isn't it better to use something which is flat in the sense uninformative in the parameters that you're looking at so that it weighs everything equally? Because like as you were saying, if you have this one crazy event and your population model does not support that, so it might give you posteriors, but if instead you use uninformative flat priors, that would not pass it.
Yeah, that's a great point. And I think I did say like the population inference is giving you the priors that you should have used in PE. I actually don't think that we should be changing our parameter estimation priors for the first step of the inference, because you're right, like especially at this point where we're still learning, what the population looks like, it could be that our population models are wrong. And so we would end up, if we actually adopted a population model in this inference before we inferred the parameters, we would end up like throwing away all the likelihood support up here, and that would be bad. So yeah, I'm not advocating to change the like the first step parameter estimation priors at this step. So yeah, great point. Cool. Okay, so let me move on to show some population models. Okay, hopefully I've convinced you all that you should start fitting populations yet. It's okay if I haven't, I'll convince you by Friday. So your population model should really be describing the distribution over all of the parameters that are going into your gravitational waveform. So these are the source frame masses, the spins, all spin degrees of freedom, the merger redshift, and really also the background cosmology that relates luminosity distance to redshift, and the binary position and orientation, tides if it's a neutron star, beyond GR parameters if you don't believe GR, all of those things. So you can fix some of those distributions. You don't necessarily have to fit for all of them. So for example, we usually assume like an isotropic distribution of sources on the sky. We don't vary that assumption, although there have been papers that have done that. For population analyses right now, we typically fix the cosmological parameters, although you can also fit them simultaneously. We just do that when we're doing cosmology. And then you can also assume some distributions are independent or separable. So like the mass distribution might be independent of the redshift, and you have the same mass distribution at all redshift. Or maybe the spin distribution, you want to write that as being independent of mass. Or you can write things as being correlated, like maybe the mass distribution does depend on redshift. So yeah, you just like write down your population distribution and also what hyperparameters it depends on. So now I'll give some example of what those different parametrizations of your population model could look like. And so the first thing, which we've already kind of seen, is a parametric phenomenological model. So these are things like power laws, broken power laws with dips, bumps, and tapered edges, Gaussians, and mixtures of all of the above. So almost all of like the parametric phenomenological models you see are just some variations of power laws and Gaussians, maybe some beta distribution sometimes. And really, we're just not very creative. Then you could go on the other end and just do data-driven models. So these are things like a histogram is kind of a simple example of a data-driven model. You do have to define your bins, but then you're just fitting for the rate at each mass, spin, redshift, bin, whatever. You can do splines, Gaussian processes, normalizing flows, KDEs even. These are all kind of data-driven models that have been used for gravitational wave population inference. And then you could go to the other extreme, which is physics-driven models. And so these are things like you have some physical parameters that describe your population, and by tomorrow we'll have a better sense of what those physical parameters are. But these are things like the initial mass function of stars, parameters describing stellar evolution, like nuclear reaction rates in stellar cores, binary interactions. These are all things that are going to affect your binary black hole population. And so for the physics-driven models, you need to forward model what your black hole population looks like for these various physical parameters. And that gives you like the mass distribution as a function of, stellar initial mass function, for example. Okay, so now I think like for the rest of today, I'll just give a bunch of examples of these. So parametric mass distributions, these are things like I showed power law in our recent catalog GWTC3, kind of like the default mass model was this power law plus peak, which is just a mixture model of a power law plus a Gaussian. The Gaussian is here. And this is actually, one of the things we inferred in the third observing run is that there is a deviation from just a power law, and one way to write that deviation in a way that still does an okay job of fitting the data is to introduce this Gaussian peak that the data find to be at around 35 solar masses. You can also write look at it in the joint primary mass and secondary mass distribution. I should also, the plots I'm going to show vary a bit in the convention. This plot is from, at both of these plots, I've taken from this recent review paper by Tom Collister. Actually, a lot of the plots I'm going to show are by Tom Collister because I just love his plots. He's great. So this is the rate as a function of primary mass at a fixed mass ratio, Q equals 1, and a fixed redshift, 0.2. So if you integrate this out over all masses, you will get a number in units of per cubic gigaparsec per year. That will, and then you're integrating over solar mass, so that goes away. And so you'll get that rate that refers to the rate of Q equals 1 systems at redshift 0.2. Okay, so that's, now we also have a bunch of the data-driven mass distributions. So this one is using this autoregressive process from this paper by Tom Collister and Will Farr, where each posterior draw here, one of these traces, is just this, like, I'm not just shaking a lot. This is what like they look like. They're just like super jagged. And so this envelope kind of gives you like the median rate you infer as a function of mass here. And then these are the 90% credible regions. This ends up looking similar, right, to something like this power law plus peak, but you still get this peak here. But now it seems like there's also a peak at like 10 solar masses. The spline model finds something similar. So this model starts from something like a power law and then adds these spline perturbations on top of it. And so here in blue is the power law plus peak model. And then in orange is their spline fit. This is from a paper from a couple years ago by Bruce Edelman, Ben Farr, and Zohair Doctor. There's this bint Gaussian process model. Also, this is from a paper by Anaria Ray, which shows here also comparing to power law plus peak, this time in orange, and then in blue is their results. This model basically just puts a bunch of two-dimensional bins in M1, M2 space, and then fits for the rate in each bin. So it's like this piecewise constant thing, but the prior on the rate in each bin is this correlated, basically multi-dimensional Gaussian like correlated prior. So there's some degree of smoothness that is brought in from the prior because the rate in each bin is correlated with the rates in the other bins and like more correlated with the rates of neighboring bins. Yeah, this also finds possibly something similar to these other ones where like there could be another peak at 10 solar masses. And we wouldn't necessarily know that if we were just doing these parametric phenomenological models unless we thought to like add in another Gaussian and fit for it. Yes.
Primary mass, is there any reason why you're not looking at the best measured parameter, something like the chirp mass, but the primary mass?
Yeah, that's a good question. There are papers that do this in chirp mass instead. I think primary mass is just more physical. So if you are comparing to like the theoretical predictions, it's more natural to do it in primary mass. I think if you end up finding features in chirp mass, it's kind of more difficult to interpret, because it's like, why would the universe make features in chirp mass? Like, that's not a thing stars should know about, but yeah. But you can do it in, like, you can also do it in total mass, for example. Yeah. Okay, and then, yeah, so looking at, that was kind of about masses. Now looking at spins, you can fit the spin magnitudes and the spin tilt, or the cosine of the spin tilt. So just to remind you the notation, this is the bigger, so we label spins the same as we label masses, meaning the primary spin corresponds to the primary mass. The secondary spin corresponds to the secondary mass. And then similarly for that's like, there's a spin magnitude, and then there's a spin tilt, which refers to the angle from the spin vector, from the orbital angular momentum axis to the spin vector. Of course, there are other spin parameters also, but these are the two we tend to look at. These models assume that both spins are drawn from the same distribution. There's not really a good reason for that, but that's what these models assume. You could fit for the spin magnitude as a truncated Gaussian. So the spin magnitudes are drawn from some truncated Gaussian distribution, and fit for the mean and standard deviation of that truncated Gaussian. It's just truncated because it has to have support only between 0 and 1, just physically for a Kerr black hole. We end up finding that spins are pretty small, although with some width to the distribution. So some spins are as large as 0.4. This is a fit to the cosine of the spin tilts. If this was flat in cosine tilt, then that is like an isotropic distribution where it's just random spins. If it was peaked at cosine tilt of 1, that would mean that spins prefer to, the most likely orientation is spins that are aligned with the orbital angular momentum. There are some hints that the tilt distribution is peaked away from 1, but is not flat, which is kind of weird. We'll see if that holds up. That would be like the most likely spin tilt is not quite at alignment, but somewhat misaligned. You can also fit the spin distribution in terms of the effective spins. I guess this is like exactly what you were asking of, why don't we fit things in chirp mass? I would say in chirp mass, in masses, we still measure the mass ratio well enough for it to mostly make sense to fit the component masses. But in spins, often we do things in effective spins just because it's very hard to get higher order spin information for the bulk of our signals. And so people also fit the effective spins. And just a reminder, so chi effective is the mass weighted average of the spins projected along the orbital angular momentum axis, whereas chi p is a measure of in-plane spins, really like proportional to, it's like how much the primary spin, how much support it has in the plane. You can ask Patricia all about chi p. And these are, so here you could fit a skew normal or a normal distribution to chi effective. This is from a paper by Sharon Benagiri. You could also fit a truncated Gaussian, in case it's not clear, I'm using normal distribution and Gaussian distribution completely interchangeably, to the chi p distribution, for example. Okay, yeah, and then for the redshift distributions, one thing that is natural to do is to fit for the merger rate as a function of redshift according to a functional form that looks similar to the star formation rate. So this is using the same parametrization as the Maddow-Dickinson star formation rate. But the star formation rate increases as a function of increasing redshift up to around redshift 2, and then turns over. Here, we don't have the sensitivity to see until redshift 2, so we're really just seeing the lower redshift behavior up to around redshift 1 of the rate as a function of redshift. And then this is also compared to the star formation, the shape of the star formation rate, which is in the dashed lines. Of course, there are more stars than stellar mass black holes that merge in our universe. Otherwise, we would like break many laws of physics. Here is a fit to essentially the same thing, but this time from this autoregressive process. The other kind of data-driven models tend to find similar things, at least on the GWTC3 data. I should say the GWTC3, everything I've been showing is based on that third gravitational wave transient catalog, which doesn't include all 300 events. It includes the first like 70 or so. Yeah, so here it ends up looking somewhat similar if you squint, that the rate was higher at redshift 1 than it is at redshift 0, but it shows that there might be some more complicated structure, like maybe it's flatter between redshift 0.4 and redshift 0, and then kind of steeper at higher, out to higher redshifts. But the other thing we look at is correlations. So I showed one plot before that kind of hinted at the correlations between primary and secondary masses. There's this paper by Amanda Farah from last year that goes into this in some more detail. Basically, what are the different pairings you can have between primary and secondary masses? So we kind of know that overall, there's a preference for symmetric systems. So M1 equals M2, that's along the diagonal here. But exactly whether some features like the 35 solar mass peak appear in M1 versus M2 versus both is less certain. So like in this paper, Amanda fit a few different models looking at whether all the features in M1 also appear in M2, in which case you can kind of see you would have like a peak at 30 solar masses that appears in both M1 and M2. Or actually, if you allow for different features in M1 and M2, what Amanda found is that it looks like the peak might only be in M2 and not in M1. This is kind of the default power law plus peak model, which lets there be a peak only in M1 and not in M2. So all of this is still kind of tenuous, but with future data, we could better understand these correlations between primary and secondary mass. One of the most robust correlations so far that has been shown with the gravitational wave catalog is the correlation between mass ratio and effective in-spiral spin. And so this was first shown a few years ago in this paper by Tom Collister and others. And here, this set of plots is showing their inference for the mean of the chi-effective distribution as a function of mass ratio and the standard deviation, or the log base 10 of the standard deviation distribution as a function of mass ratio. And so they basically fit a model where this chi-effective distribution was a Gaussian with some mean and standard deviation that they allowed to vary as a function of mass ratio in this kind of linear way. And they found that it looks like the mean of the chi-effective distribution is larger for smaller mass ratios. So more asymmetric systems tend to have larger positive chi-effective than more equal mass systems. That's what's shown here. This is the marginalizing over the posterior. So this is kind of the mean inferred chi-effective versus Q two-dimensional distribution. This is from the Collister et al. Paper. And then in blue is from this work by Christian Adamsewicz and Eric Thrain, where they basically also fit for a correlation, but this time instead of having this like linear correlation in the mean and standard deviation of chi-effective as a function of Q, they fit the correlation with a copula model, but they end up finding something pretty similar there. Oh, yeah, let's start here.
Do we have an understanding what are the mechanisms behind?
You mean the astrophysical mechanisms? Yeah, I will talk a bit about this tomorrow. I guess one thing I should say that I couldn't find this in a plot, but really it's not necessarily, so in this makes it really look like it's this correlation in the mean of the chi-effective distribution. The data is still kind of consistent with it being a correlation in the standard deviation. So basically where the more unequal mass systems have a broader chi-effective distribution than the more equal mass systems, that makes a lot more sense astrophysically if you think about hierarchical mergers. I'll explain this more tomorrow. But this actually, like some correlation between chi-effective and Q, I think the first time I saw it at least was maybe in a paper by people here, like Matthias, I think you were on that paper where the explanation is that only one of the black holes in the binary is spinning because it's got spun up by tides. And so something like this you might expect just from thinking that like chi-effective is a combination of the two black hole spins and it depends on the mass ratio. Like it's a mass weighted combination of the black hole spins, so that if only one black hole is spinning, you would expect some correlation. This kind of makes it look like if one black hole is spinning, it's the more massive black hole in the binary, which is a little strange, but not too unexpected, I guess. Yeah, and do you have a follow? Okay, yeah, maybe back there. Yeah. Yeah, no, that's a great point. And that's why when this result appeared of this correlation between chi-effective and Q, it was like so concerning for that reason, because we don't think it should, like in the hierarchical Bayesian framework, that shouldn't like we're not, any correlations you have in individual events should not manifest in a robustly identified population level correlation. It might lead to something that's consistent with that correlation, but it shouldn't like rule out an anti-correlation. Like that's just not, I guess from a statistics point of view, like that shouldn't happen. But you're right that this kind of population level correlation is very similar to the correlation that we find for individual events. So in the original paper by Tom Collister and others, they went through so many tests to show that they weren't just picking up on this parameter estimation single event correlation. But yeah, that's a great thing to worry about if you see something like this. And yeah.
With respect to the previous question, you just mentioned that the black hole is spin off by other effects.
Yeah.
You mean like the progenitor star or like the black hole itself?
Okay, yeah. So I will hopefully talk more about this tomorrow, but what I mean is the progenitor star. So so essentially when you, at the stage where you have fairly tight binary between the firstborn black hole and the helium core of the progenitor to the second-born black hole. At that point, that core can get tidally spun up, and then the assumption is that that core rotation then goes into the black hole spin. Okay, were there any, yeah.
Know how to replace. It seems to me that the field is in a big price. If I go on slide 15 to slide 24, it shows
15.
10 plots pretty much. And I think almost every one of them was already refuted by the field.
Oh,
So we can do it. So this one, it just showed that you don't expect any mass fit about like 50 solar masses, and we've seen like 5 of them.
yeah.
So if you go to another one, it's not against you. I feel that we are in a big crisis. There's something wrong. I don't know what to put. So for example, this plot as well, after 90 solar masses, they're already there. The plot on the right expects no Q below water. We already have events over there. So if you look at the years, every plot that is filled before 03 has been refuted by the 03 data. So now it's a question. Do you think that there is any way to make this under control?
Yeah, so I guess, yeah, so for like this plot, this is just my fault because I just put a sharp maximum mass cutoff in the power law and just never put, like never fit a population model where the rate goes to 0. Like that's just, yeah. Yeah. Yeah, no, so yeah, no, so that's a great question, because I think that's really the point of like these more data-driven models. When we have these parametric phenomenological models, their lifespan is inherently limited because they're really just designed to, right? Like even, I guess here, like, okay, it's just a power law with one peak. So if there's another peak out here or another peak down here, this model's never going to find it. And you might get tighter and tighter uncertainties when you're fitting this model. And you might think like, oh, you really understand the merger rate at 20 solar masses really, really well if you're just fitting this model. But it's just a bad model because, you know, I mean, it's definitely a bad model. Like it would be so weird if the black hole mass distribution followed a power law plus a peak. So I think that if you really want to have like the most faithful fit to your population that will stand the test of time, you really need to go for these more data-driven, non-parametric methods. So I think something like this.
People put upper limits when they think, okay, here I don't know anything.
Yeah, yeah. Yeah, so upper limits are, so you still need like some prior, which would extrapolate from where you have when you have some constraints to where you're transitioning to having upper limits. Or another way of saying that is you can always put an upper limit on the merger rate, but then you have to assume what the population looks like. So for example, like we could put an upper limit on the merger rate of subsolar mass black holes. Like we are doing that, right? But then you have to say, okay, well, what do you think the mass distribution is of subsolar mass black holes? Because that's going to affect that VT that you get. If you think they're all close to 1 solar mass, you're going to get you're going to get a more a stricter upper limit, like a smaller upper limit than if you think, oh, they're all actually around 0.1 solar masses. So that's like where even our upper limits have uncertainties on them. But for example, like in these models or like in this binned Gaussian process model, you can add bins at higher and higher masses where you haven't seen anything, and you'll get like very, very uncertain rate measurements that will just be set by the prior, which is setting how you're extrapolating from lower masses out to higher masses, because you're assuming that the higher masses are still correlated with the lower masses. So something like a bin Gaussian process will give you kind of a safer upper limit on where you haven't seen any events than something like a power law with a maximum mass. Okay, great. So where were we? Okay, this correlation. Yeah, so people have also found correlations between spin and mass. This part of the literature is still, I think, very active and probably still pretty confusing if you're new to it, because there's a lot of different claims out there. But here are just like two that I'm highlighting for the sake of these slides. One is this paper by Jackson Godfrey, Bruce Edelman, and Ben Farr, where they basically allowed for a different spin distribution in this 10 solar mass peak compared to this continuum. So in blue is like one population, one subpopulation, and in pink is like this other subpopulation. And if you allow those different subpopulations to have different spins, this is the spin magnitude they inferred. So like in the peak, perhaps smaller spins are favored, like it's like a more sharply peaked at 0 compared to in this continuum. And for the cosine of the tilt angle, perhaps in the peak, things are more aligned, more preferentially aligned than in the continuum. And so in this paper, they pointed to this as maybe saying that the origin of this peak is isolated binary evolution. If that doesn't mean anything to you yet, then hopefully it will in lecture 2. But similarly, there's another correlation that's been found. So I guess in case it's not clear, like different parts of mass parameter space having different spins is equivalent to like a global correlation if you just looked at, the spin distribution as a function of mass. And so similarly here, this is looking at the fitting similar to like the Q chi-effective distribution right here. It's the log of the standard deviation of chi-effective and the mean of the chi-effective as a function of primary mass. And this is from a paper by Fabio Antonini and others that just came out like a few weeks ago, I think. Their first paper in these series came out like earlier this year, but now they're fitting for this non-parametric correlation where the shape of the correlation, like the shape of these curves, is a Gaussian process. So it's pretty flexible. And they're finding that the mean of the chi-effective distribution might not change that much with mass. Maybe it's a little bit more positive at low masses and maybe more consistent with 0 at higher masses. But the standard deviation really does. So at higher masses, particularly above like 45 solar masses or so, they're finding that the chi-effective distribution broadens a lot, which is consistent with higher spin magnitudes. So above 45 solar masses, black holes seem to have higher spin magnitudes than at lower masses. And this is actually a very exciting result because I think it hints at the parent stability mass gap being at 45 solar masses. And again, I'll explain more about that in the next 2 lectures. I should also say at very low masses, the uncertainties just blow up. So this isn't a measurement. This is just recovering their prior. We just don't have enough events at low masses. Okay, and then another correlation that people have studied is between spin and redshift. There is some hints at the spin distribution also getting broader at higher redshift compared to low redshift. So this is in this paper by Sylvia Biscovenou and others from a few years ago. where this is the chi-effective distribution at very low redshifts, and then the other colors show it at increasingly higher redshift. So you can see it seems to kind of broaden. This is from a paper we did led by Simone Bavera, where this is like a very specific physics-inspired model. And we didn't conclusively find the same thing, but we found hints that maybe there were larger chi-effective preferentially at higher redshift than lower redshift. Yes.
Based on this plot, how can you confidently chi-effective negative events should we find the outcome?
Yeah, that's a good question. So there is, okay, so I guess is your point that if they are more common at higher redshift, we should find them more in O4 because we're probing higher redshifts compared to O3, or just in general, the fact that there's support for.
Yeah. So chi-effective, if you look at spin 0.1 versus minus 0.1,
Mm-hmm.
the astrophysical selection effects are really different. And if you look at the actual spins for you have like the binary black holes are voting with the things, there's like 20 positive, 0.
Yeah.
So I wonder, how do you get the distribution?
Yeah, where does the support come from? Yeah, so it really is coming from, it's like a true population result. It's coming from stacking a lot of events that have somewhat negative chi-effective. The problem is, I think I showed this earlier plot from Sharon's paper. Like we think the chi-effective distribution looks something like this. So it definitely has a longer tail to positive chi-effective. And there is support at negative chi-effective, but it's really, really small negative values. So it's perfectly consistent with like the negative tail just extending to like negative 0.05 or something. And our single event parameter estimation measurements are so broad that even if we had a bunch of events with chi-effective negative 0.05, they would always have support for positive chi-effective. So finding an event where the single event PE rules out 0 is very tricky.
So this plot, I understand. I should interpret the negative chi-effective as an upper limit.
Well,
if I made all beams in terms of 0.1, the beam left of 0 is not like rejected, but it is already like there's some tied up.
Yeah, well, arguably, yeah.
Then here it's not reflected that this entire prediction minus half chi-effective is based on events we've never seen. It's not clear for this plot.
Yeah, well, this plot doesn't allow for like this skew chi-effective distribution. So you're right that like the tail, this is only allowing for chi-effective distributions that are symmetric about their mean. So I agree this probably.
It would improve the probability for the negative.
Well, the mean can also change. So yeah, you can shift things over, but if you do have a skew, then it will, then you can get a model systematics here. But yeah, I will say that we do have enough events where we are able to distinguish 0 from negative 0.1. And so the fact that we seem to have events like between negative 0.1 and 0 on a population level is informative, even though we can't point to an individual event that is definitely in that bin just because of measurement uncertainties. But, oh, I realize I'm out of time, but I think, okay, I just had one more slide about correlations between mass and redshift, which we don't find, but we look for them, obviously, because that would be interesting. And then I've shown phenomenological parametric and data-driven models. I haven't really shown any physics-driven models, but there are papers that do this. So for example, there's this recent paper by Storm Columns where they essentially used a normalizing flow trained on a bunch of population synthesis simulations. And then, so for these different like physics parameters, like the spin, the birth spin of black holes and like the common envelope efficiency, that gives them a predicted distribution of black hole masses and spins. And then by comparing that to the population and doing the same hierarchical Bayesian inference, they're able to fit like the birth spin of black holes and the common envelope efficiency. And also this is a mixture of many different channels, so they can constrain, which channels are contributing. And I think I just have one more slide. So showing the pros and cons of the different population models. So for data-driven models, the pros is that it's a reliable description of the population. This is like the most reliable description of the population you can have. The disadvantage is that it can be challenging to interpret and also can be prior driven where data is sparse. So that's kind of what I was mentioning earlier, is that especially when you're like extrapolating to parts of parameter space, a lot of that is driven by your prior. So you just have to be careful. For physics-driven models, the main advantage is that it's interpretable. It measures the parameters that we actually care about. Like if we want to do astrophysics with gravitational waves, this is what we care about, is we want to measure physics. The cons is that it can be computationally expensive, but more importantly, there are systematic biases that could enter your inference from missing physics, because we just don't have a perfect description of the physics underlying the formation of stellar mass black holes. And then parametric phenomenological models are, depending on who you ask, the best or the worst of both worlds. So they're easy to write down. They can be the computationally cheapest, and they are somewhat reliable and somewhat interpretable. The disadvantage is that basically they're somewhat unreliable and somewhat uninterpretable. And they can be prone to systematics, but they are easy, so we still use them. And I think, yeah, that is my last slide. So I think we're out of time, but I'm happy to either take more questions or just chat during the coffee break.